Okay, my wonderful, outstanding friends. I got this morning from a friend of mine, Howard Bankston, and he said, check this out. Scientists announced a Large Hadron Collider found something for the first time ever. And he claims to think that they're watching what I'm doing. Now, that could be, I don't know. I just started into this. I got into it a couple of minutes into it, and I said, well, I'm going to do a video on it because I don't know exactly what they did find. But if it's in the Large Hadron Collider, they're using enormous particles and smashing them together. They get all kinds of debris. What they are finding is bits and pieces of particles. But my theory is that there is nothing that exists other than electrons. And electrons are not just a negative little glowy part. They have a dark side, the muon. That is what they've been looking for. It's attached to an electron. They can see them. They just didn't know they were attached. And the two of them together make photons. I've shown it a million times. 1,839 electrons actually equal what they would consider to be a proton. And then they get bigger and bigger and bigger. And this is what really an atom looks like. And this could be the core of a hydrogen, which is only one proton. But the proton is made out of 1,839 dipole electrons. So you have a dipole nucleus, and then the electrons are dipoles too. So they're out here interacting with a dipole nucleus, and they want to get into the core of the nucleus, and it will only allow them at a quantum distance, which is, these are going to push away just enough to keep them at like 5 angstrom units or whatever, a certain distance away. And that's what quantum physics is all about. Now, we're going to go into this I'm just going to play it, and I might stop it and make comments here and there, but let's just take it from the top. Okay, so let's get right into it. This is Unexplained Mysteries. They got 1.47 million subscribers. Now, this is about, they announced something from the Large Hadron Collider. I'm not sure exactly what. I think it has to do with ghost particles. And let's see what they have to say. Now, I am a fair user, which means I can show these kind of things without copyright infringements because I'm just using it for educational purposes and for, you know, to explain my side of what they're saying. Now, I don't know if my side might be exactly what their side is. I have no idea. We're going to find out in a minute. So here goes, and I will comment as we go. Here goes.
The universe presents us with a huge range of theories, concepts, and research opportunities. Everyone views the universe differently, and whilst some believe there are more than one, some choose to not ponder the overwhelming vastness for too long, and some dive headfirst into all the latest studies and breakthroughs. We are all part of the same universe. Exploring the world beyond our homes on Earth can seem impossible to comprehend, though with every bit of research we draw a little closer to unravelling some more of the puzzle. So today, here at Unexplained Mysteries, we will be taking a look at 3 interesting physics discoveries that have developed our understanding of what is out there, from the smallest particles to the biggest stars to searching entire galaxies. Physicists detect ghost particles in the Large Hadron Collider for the very first time. Particle physics may not sound like the most interesting concept, but there are some fascinating developments happening in the field as of late November 2021.
Let me just explain something to you. What they are doing is taking huge pieces of matter, protons, which to me are huge, because I work with light. Light is, you know, light is everywhere, and you don't see it, it's just everywhere. Now, protons, they're a whole different story. You're banging into them. And when they bang together, they explode like an atomic bomb. Look at all the pieces. When we explode, when we hit ours, we just have like 4 little pieces that come apart. And we can see where they came from and where they go to. Now, this is, they call them ghost particles. I'm going to show you what the particles are that they can see in this debris and don't realize where they came from. Alright, this is what they're trying to get to, is this right here, where the black balls separate from the white balls and turn into showers. The white balls are the showers, the electron showers. And the electrons are the things that we see. They glow, they reflect light, they create energy, they're static, they're electricity. The black part here, the black ball, is what they call a muon, and it is attached to the white. It's the positive to the negative, basically. This is the only part we've ever seen, is this. Now, the reason it's showering like this is because of the venturi we created. Now, to get to this point, we had to already accelerate light. That's when it split and divided and then came back together. This is fission. That is fusion. In between is raw energy. Should be 207 times as powerful as when it started. Now, here is the transfer of energy. Bip, 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 red pulse laser. Everything in front has to glow a little bit because that wave, which is a magnetic field driven by a magnetic particle, just like a magnet has a field around it, has to go through the air. When it does, all the other magnetic fields of all the other magnetic particles in the air, and every gas is a magnetic particle, has to concussion cause glow. Extreme concussion causes extreme glow. This is the venturi right here. This venturi is an accelerator. And when it accelerates the particles, it not only accelerates them, crushes them through a tiny, tiny, tiny little slit here. In the process, it has to accelerate the light. It accelerates. You can see it. The wave is actually just like a jet fighter. It's coming out of the wave, and now we're seeing the particle. And right here is where we actually see the particle prior to it splitting, as I showed you before. Here's the white-black particle. That's what they are together, just prior to them exploding. And as they concuss, boom, they just go into explosion land. And of course we have all the Higgs fields and so forth. It's all the same stuff that CERN wants. Only we're using light, so we can see it. These are no ghosts to us. These are obvious particles that are in the air. They are particles. They accelerate. I can show they also slow down. This is blue as it's coming in. And then slowing down up here. You see it concussing. This is there's a whole new realm to light than we were originally taught. So, and Bohr is wrong, Hubble was wrong, Einstein was wrong. They're all wrong, because light is a particle that is a dipole, and and it's also two electrons back to back. I might have showed this before, but you're going to see it again. Everything there is a dipole. There is no such thing as anything other than a dipole, except for instants in time like this. Just a brief instant in time, they come right back together. So it's called dipole electron flood theory. It solves 100% of every single material interaction. If you can come up with anything at all, red spites, blue spites, all of the different effects of light, and we don't know where we are in a universe, because light, it's ubiquitous. It's everywhere. If this is particles, there's absolutely no question they're particles. They fill the space, and I have to be particles. They come down from the sun. They hit solar panels, and they drive other electrons out to create electricity. There's no question what it is. It's just that we have to understand it fills the space. There's no such thing as a vacuum. So that changes everything. That changes the heat, why we're so overheated in the ionosphere, 2,700 degrees. It shows why the sun is millions in a corona and only 7,000 on the surface. We're scrubbing through all these particles in space, just exactly like you'd scrub your tires down a pavement. And they heat up. And the more we fluff up, which is the expansion of gases, combustion and so forth, that is what is making it scrub harder and harder, and all the turmoil. And anyway, that's just part of the issue that we're going to be discussing here today. Alright, you saw this, and you saw these were attached prior to them exploding here at the venturi. Now, here's what they look like just as they explode. Alright, that's the box of particles. There's two whites, and two blacks. The black ones never change. They don't grow bigger, they don't grow smaller, they don't concuss, they don't absorb, they don't reflect, they don't emit, they don't do anything. They just want to be glued to the white ones. The white ones expand and puff up. They contract as they lose energy. They fluff up as they impact going forward. Remember I showed you all those particles that were getting impacted? Those particles right there. That's why this is glowing. Anytime you have push to shove, you're going to get glow. This one's not pushing anybody. The black one's in the way of it, so it's just going to turn into nothing. And then when this one's so overcharged, blip, it'll flip. That one will go front, and it'll start to charge, because it will be the one concussing. And that's the particles we're talking about. Okay, so here we go back to the ghost particles from the Hadron Collider. Now, let's open this back up and see what they have to say.
Bound to pique the interest of even the least scientifically minded among us.
Let me just back that up a second. You can see what they're dealing with here. It's gigantic quantities of particles. You saw it. We were dealing with one little particle. A totally different situation.
This may not sound like the most interesting concept, but there are some fascinating developments happening in the field as of late November 2021. Bound to pique the interest of even the least scientifically minded among us. Particle physics aims to gain insight into the universe by looking at the smallest units we can in order to gain an insight as to how things work on a much larger scale. However, not all particles are made equal. Some are much more elusive and much trickier to study than others.
All right, he's wrong. They are all made equal. They are all these particles right here. And they consist of the two smallest elementary particles there are, a muon and an electron, which we would call neutrinos. And as a package, I would call them an electron. Nobody's ever seen the dark matter before. So let's continue on to see what they have to say.
Making them all the more exciting. Back in school, you might have discussed subatomic particles, looking at electrons with a negative charge, protons with a positive charge, and neutrons with no charge, all found within an atom. Well, a neutrino is not too dissimilar to this. Neutrinos are subatomic particles that are fairly similar to electrons. However, they differ in two key ways. They have no electrical charge, and their mass is so minuscule that it could even be considered to be zero.
All right, both of those things are wrong. The minuscule charge, absolutely, is tiny. The size of them is virtually nothing. And so he's correct. They could almost be considered to be nothing. But if you took each neutrino, and you would have about 1,839 of them in one proton. All right, that's the equivalent number. So its actual atomic mass unit is 0.0005458, something like that, atomic mass units. But it's very small, 0.00055, say. And its charge is very small too. But it is really 1 electron volt, because we're talking about 1 electron. All right, so 1 electron volt is what the energetic value of this particular particle is. We saw them back to back, which is each electron. I consider that to be an electron, but it consists of the two particles, and another one back to back of it, like 2-bar magnets make the photon. That's what we're seeing. These will bounce off of things because they're semi-neutral. They'll hit something, they may drive a charge, but then they bounce off as light. This one usually incorporates. It goes in and it hits and it sort of glues in there because it wants to attract into something that will accept it. This, it will bounce, and that's what we see as light. That's why we see all the different colors of light, because it's hitting different things that have a different bounce ratio to it. Depends on what it was hitting and how strong that particle was moving, and what it hit, how bouncy that impact zone was. That's what creates all the different colors of light. And when you get into just one single proton, they would consider that the atomic nucleus of a hydrogen 1. Well, it's not. The nucleus of a hydrogen is 1,839 little tiny electrons all glued together. All right, that's what they do. And then so now you have a dipole, and then you have a dipole particle, which is another electron, because they're also dipoles. So now you can fulfill all of the requirements of the quantum theory: gravity, dark matter, the whole 9 yards. It's all here, 100%. Okay, I jumped back. This is maybe going to take a while. I went back, and they're talking about neutrons, protons, electrons. No, every single thing is made of electrons. I just showed you. That is, every single thing is made of that. It's just bigger and bigger particles in bigger and bigger chunks. And then when you start to get into your atoms, the nucleuses are just bigger balls of these electrons. Bigger and bigger and bigger and bigger and bigger. It starts out the smallest one, and it gets way up here into the big gigantic particles that have bazillions, I mean literally hundreds of thousands of electrons, not just 30 or 40 or 100 protons, no. Because you got to multiply it times 1,839 for each one of your protons. All right, because a proton is 1, and it's actually 1,839 electrons. So let's just continue on forward. I hope this is making sense to you. Yeah, in other words, the basic particles there are is that electron, which is made of an electron neutrino and a muon neutrino. And the two of them together, the black and white ball. Those are the two most basic particles that exist that I know of. Although we did find one that was very strange. It was a reverse spinner, I believe. I have pictures of it. Anyway, let's go back to here. They're talking about photons, neutrons, electrons. They're all made of the same thing, dipole electrons.
Might have discussed subatomic particles, looking at electrons with a negative charge, protons with a positive charge, and neutrons with no charge, all found within an atom. Well, a neutrino is not too dissimilar to this. Neutrinos are subatomic particles that are fairly similar to electrons. However, they differ in two key ways. They have no electrical charge, and their mass is so minuscule that it could even be considered to be zero.
This flashlight can burn through anything.
Okay, we're going back again to where they're talking about electrons, neutrons, and protons, which do not exist. They are just accumulations of dipole electrons. Now, here we go.
Electrons with no charge, all found within an atom. Well, a neutrino is not too dissimilar to this. Neutrinos are subatomic particles that are fairly similar to electrons. However, they differ in two key ways. They have no electrical charge, and their mass is so minuscule that it could even be considered to be zero. What is most unique about neutrinos is the sheer quantity of them. We have billions of them moving through each one of us right now. They are the single most abundant particle in the universe.
They are all the particles that are in the universe. That's all there is. They are the electrons. That's all there is. And these are the neutrinos. They call them muon neutrino, electron neutrino. And when they say they're moving through us, they're bouncing off and they're interacting with us. But they think they're just going right through us, and it doesn't hit anything at all. That's not true. I showed you. Well, let me show you one more time before we get back to this. Now, here's what you have to understand. There could be an overwhelming number of these little black balls everywhere in the universe. They could just be saturated with them, which are the muons, the muon neutrinos. Because we see the muon neutrinos leave the white showers. The white showers go crazy, and then the black balls come right back. Now, I don't think they jumped over here and reattached over here. So the only thing I can take away from this is that these white ones are finding new black ones over here that were just laying around waiting for some white guys to show up to attach to. That's all I can take from this. This is fission. We know that black were separated from the white ones. This is fusion. We know they're coming back together. So that is, and you look at the increase in energy. From back here, where there's almost no energy at all, up here it's just vastly increased in energy. And I believe we can get free energy right there by putting a collector right in here. This is just as simple as can be, almost nothing for the laser. This is virtually free. It's just a design of a couple of pieces of metal. And then you have your little collector here, which is almost nothing too. You can increase this energy 200 times and then just drain it off through, what we can use right now. We have all kinds of ways of dealing with the energy once you get it. This is the key, getting it, and here you get it. Alright, so don't forget, this is not my words. This is CERN and Fermilab. They find the muon, which is the black ball, attached to the electron neutrino, which is the white ball, and then when they slam into a new medium, they explode, just like you're seeing right here. Now, they only see this occasionally because they have to have them hit just in a certain way that they can separate as we see, and then they just see them in bits and pieces. Now, in the Large Hadron Collider, they're seeing just a spray of everything, and they're seeing the black and the white, but it's just they're seeing them. They just don't have any idea where they came from. It's like we can see this in the green as well. The red is just exceptionally easy to see because there's very little power to the red. Here's the red coming down and getting sucked in. Hold on, here we go. All right, you see it? It's coming in here. At first there's very little energy, and there's no energy whatsoever unless it's directly in line with the Venturi. And then it lines up and shows the particle exactly as it is, and then the particle explodes over here. It does the same thing with the green, only we can't control it the way we can the red. Alright, green is much more powerful than the red, but you can see the white and the black separating. So it's doing the exact same thing. The black ones are all over the place here. Now, the Venturi was askew a little bit. All we got here was white. You see that? There's no black whatsoever coming on this side. None. Zero. And the black balls are heading this direction. So they separate, and we can, what this tells me is the design of the Venturi is absolutely critical. The other one, it came through just nice, and, the black ones that went this way and that way, and everything was fine. This one here is somehow, it's like bouncing off of, the design is critical. Somebody's going to have to figure this out. And I can see all this is two round pins. And I think it's going this way, basically, coming up. See, they're getting wider up here and narrower down there. Now, whether that affected this, I don't know. Maybe one of them was out like this way. Maybe they're side by side. I don't know. Maybe they were going this way. A little bit of a twist out. But Rod played with this. He did so much work on this. It's unbelievable. But there's no question you can see the black is separated from the white. So we know this can be done. Can we tune it correctly? And the question, the answer to that is absolutely. It's just figuring out what's the distance, how wide should it be, how round should the pins be, how long should they be, what metal should they be made out of, how far away should the laser be from the Venturi. The rest is just it's an exercise in simplicity, beyond simplicity, to achieve something that is just unbelievable to achieve. As far as I can see, the cost of components here is almost nothing, literally almost nothing. And the gain of energy should be over the top. Over the top. And it should be free and easy to use and portable and everything else. No grid required, nothing. Okay, back to the Large Hadron Collider. Now, my claim is that all particles are made of electron neutrinos and muon neutrinos, which in my mind form what we would always have considered to be an electron. We never saw the dark part. We always saw the glowy part. We could make static, we could make electricity, we could make lightning, we could make heat, we could make light. We could do everything with this particle, but we never knew about the dark part. All right, now, they think these neutrinos, or specifically the muon neutrino, I believe. Just pass through everywhere. Now, they may be everywhere, but I don't think they just go flying through you everywhere. I think they just collect in the center of mass. The center of mass will pull in the darkest particles, and it will always, always, always be coated with 100% white on the outside. That's why we've never seen inside. Here's what an electron looks like, or a nucleus looks like. Remember I told you, it's nothing more than a ball like this. And every one of these is an electron. And that's all you see is a little glowy ball. However, inside that glowy ball is the dark matter. And that's where it is, right in the center. Oop, see it pop out? Now that would be the dark matter. That would be where all the dark parts would collect on the inside, and all the white parts that were attached to them would surround it because they want to get away from each other. That's the nature of every single particle there is. Now, they're going to be talking about, well, I'm not sure what they're going to be talking about because I haven't watched it yet. But we're going to find out in a second. I believe they're going to be talking about the neutrinos and how they are everywhere in the universe. I think that's what I just heard him say a minute ago. Hold on. All right, it's just backed it up a second or two. Here it goes.
What is most unique about neutrinos is the sheer quantity of them.
See?
We have billions of them moving through each one of us right now. They are the single most abundant particle in the universe. However, despite the huge numbers and them moving through the universe at quite literally the speed of light, it is very rare that a neutrino interacts with any sort of matter, making them incredibly difficult to detect. Due to their hard-to-prove nature, but us knowing that they are there, they have earned the nickname ghost particles, though their supernatural status may be diminishing in light of a new study. The Large Hadron Collider, the most recent addition to the CERN accelerator complex, is the world's largest and most powerful particle accelerator. It works through superconducting magnets and is based in the European Organization for Nuclear Research in Switzerland. Jonathan Feng, a physicist with the University of California, Irvine, the co-leader of the Phaser collaboration, said, prior to this project, no sign of neutrinos had ever been seen at a particle collider.
This flashlight.
All right, they've never seen them at the particle collider, but we've shown them. Okay, so here we are talking about this gigantic machine and what they're doing to try to create these neutrinos.
To this project, no sign of neutrinos had ever been seen at a particle collider. 6 neutrino interactions were detected by the collider and were spotted using the neutrino subdetector, Phaser New. This research shows us the sheer capability of the $4.75 billion machine and opens up
$4.75 billion. Yikes. We spent less than $500. I showed you that, as far as I'm concerned, we showed the neutrinos exactly what they're looking for. And we started with light, so light is basically one of the smallest particles there is. Then we showed it was a particle, then we showed it could accelerate, and then we showed it could split. And then we showed that's fission, and then we showed it's fusion. So I think for less than $500, we had some pretty good results.
new doors for researching the little-known neutrinos at such high energies, hopefully letting us continue to dive deeper into their roles, purpose, and structure. While we have not detected neutrinos in any particle collider before now, we have managed to see them interact very rarely in some other circumstances.
All right, I'm going to talk to you about how they do it. They actually just collide accidentally off each other and then spit out the neutrinos, or the muon neutrinos and the electron showers. They have seen that happen, but they really don't know why, to be perfectly honest with you. And what it is the fields that surround these particles are magnetic fields. They're impacting their fields, and it's such an enormous amount of concussion. You get all of that radiation. Now, I'm trying to figure out what that radiation actually consists of, because it's not the particle itself. Like, what is an electron shower? I showed the ball of, well, it's like this. Here's what happens. Excuse moi. What happens is you got that black ball attached to a white ball that can fluff up as it charges, or it can discharge and get really tiny. And because it can get really tiny, it can squirt through that venturi. That's why we get the showers. And the black ones can't get through. They don't concuss, they don't absorb, they don't emit, they don't reflect, they don't do anything other than gravity. They pull the white ones back. So the black ones get out of the way, the white ones squish through there, and they come out in the showers. And so it's like, these must be much, much heavier, is all I can take away. They say it's 85% of the universe is dark matter. As far as I'm concerned, that's dark matter. Because it conforms to everything they say about dark matter. It doesn't emit, it doesn't absorb, it doesn't react in any way whatsoever other than gravity. This is exactly what we saw. Exactly. And I now add to the fact that dark matter cannot compress. That's why this white one got through, squeaked through that little venturi. This can't compress, so it couldn't get through. So there's another thing you can add to dark matter. And muons, because they are the same. Don't forget now, I showed you the box of particles, the black and white ones attached together, and how they splay apart and explode. Now, these are the particles they're talking about, the muon, neutrino, and electron neutrino. This is what they're looking for. This is the smallest particles that exist. Only this one here is the black one. The muon neutrino is the black one. This is the little squishy white one. All right, and they're attached like this. When they come in, this one squishes and smashes all the other white ones out of the way. Get out of the way, get out of the way. And that one says, I'll come back to you when I can get around the other side and we'll get back together. Now, I believe there's a whole batch of black ones over here just waiting for the white one, for any white one to be available, and boom, they're going to grab right onto it. I believe that's the case. And I know for a fact that they were attached here together, particles back to back, as I showed you. And they separated here, no question whatsoever. White electron showers, absolutely no question whatsoever. Black muon balls, no question whatsoever. Reattached over here, no question whatsoever. Fission, no question. Fusion, no question. What they say is 207 times energetic value right there versus before they split. I can't verify that, but that's what I've been told. All right, so don't forget now, we got these neutrinos coming out of our earlobes, and we know really how to do this, but that was 6-7 years ago. The whole operation has been broken down, and we're not going to do it again. Somebody else is going to have to do it. If they can do this stuff, for less than $500, we did our stuff. And I would hope somebody would say, let's give it a try and see if we can recreate it. They could spend $10,000 to whatever it takes to see if they can make this work. And I think they've done for $10,000, I think they can make it work easily. You know, if somebody knows what they're doing and they don't do this kind of stuff. This here, I mean, that right there is $10,000.
Subdetector, Phaser New. This research shows us the sheer capability of the $4.75 billion machine and opens up new doors for researching the little-known neutrinos at such high energies, hopefully letting us continue to dive deeper into their roles, purpose, and structure. While we have not detected neutrinos in any particle collider before now, we have managed to see them interact very rarely in some other circumstances, namely IceCube, found in America, Super Kamiokande, in a Japanese research project, and Mini Boon at Fermilab, Illinois. These all used highly sensitive photodetector arrays. When a neutrino interacts with other particles in entirely dark environments, light is produced in what is often described as a shower of light.
It's exactly what we're showing. In a dark environment, in a we're using the exact same technology they're using there to see the pictures of light that we're showing. And I believe they're going to be able to do this pretty soon themselves if they keep paying attention to what I'm showing them.
This light is what the photodetector arrays can pick up on in the rare instance that neutrinos do interact. While this research is great, there are of course limits in how much we can learn from this. The next step was to try to study the ghost particles in particle colliders. The collider neutrons, produced from the decay of hadrons, have extremely high energies.
Alright, I'm going to cut this off for now because I know I'm going to go very, very long. But it sounds like they're trying to justify neutrons and protons and all that other stuff. And it's not true. They need to look at light as the tiniest particle there is. They know that they can break down protons into these tiny little bits, but they think I don't know what they think, to be perfectly honest at this point, because they say we're looking for the elementary particles, but we got this one, and we got one a little bigger, and a little bigger, bigger, and they're all elementary particles. No, they're not. The one that started right here was the elementary particle, the one little tiny one, which is this one right here, as I showed many, many times. And it is made of a muon and an electron neutrino. All right, when they're just stuck together, that's what they are. And we would always call that an electron. I call it an electron because it does exactly what an electron does. You can make static, you can make lightning, you can make electricity, you can make, they add together and together and together until you get to protons. And for some reason, at 1840 or so, 1839, they're pretty much stable. But when you get out of that area, as Mendeleev's chart shows, when you don't stay in that, 1840-ish range, it becomes unstable. And then you get isotopes. And then you get nuclear decay and radiation. Because the particle in its ballness is not stable enough. It's not vibrationally stable enough to maintain that structure. And this is seen very easily in salt experiments.
Roger?
Yeah. All right, this is Bruspup. This is fabulous. Amazing resonance experiment. Here's what they're doing. They're going to take this plate here of steel and they're going to vibrate it so vibrationally, and this will show the hertz rate, how many times a second it joules up and down. All they're doing is pushing electrons up and down. That's it. That's it. Now they're putting salt on here, which is a polar molecule, and it is going to shake those things up and down. And then they'll just find themselves a certain frequency where they feel comfortable. That's what I'm talking about. Is watch. Now this is Nikola Tesla. He talks about vibration. It covers everything. It's always vibration. Now, this tells you how many times a second it's shaking. Salt is a polar molecule, NaCl, on that metal plate, see? And all it's doing is shaking the electrons up and down fast. The pitch depends on what low frequency you get. Watch, I'm going to stop it as it homes in. Bang, all right? This is 345 hertz. That is the lowest frequency. This gives you basically the structure of an atom that has hydrogen and helium, basically. That's as much as it can hold, which is 2 or 4 electron orbital centers. Now, as you go up, you go into what's called the rule of 8. The rule of 8 will surround it with 8 orbitals. Okay, so now they're going to go up in frequency. Now watch what happens. And it's only when it hits that frequency they become stable. All right, there's 8 of them. You see them? 1, 2, 3, 4, 5, 6, 7, 8 around the central nucleus. So it starts with 2 around here, basically, is what they say. And then and this is a pattern I see, and I see it all the way up through. Look at this patterns. And if you figure it out correctly, you can look and find these push to shove places, and usually it's with the 8 of them. And I have found this in the light experiments as well. You see, you could find these patterns all the way up, and these are just more and more frequencies. Yeah, so we're up to 4671. Then they go up to here. Look at how elegant these things are. And that is nothing more than polar fields pushing and shaking until they all of a sudden say, boom, all right, I'm okay with this 5201, let's lock in. And it'll get nice and crisp. Wow, so, look at that. Isn't that fabulous? Now I'm going to show you what quantum is, because you can see these things in little toy looking things. Okay, this is Latham's crazy machines. Very, very cool. They have a brass ring, and then he has all these negatives surrounding it. Then he's going to put a positive core. That's my electron flood theory. The core of all atoms in their nucleus will be a positive dark matter. And then surrounding it is going to be the white particles, which we always see. So it'll be basically look like this. He's got a flat plane looking thing. So now he's going to put the core, which is the positive. And if you could break them apart, here's what would happen. You'd see this, you'd never see inside here. So all you see is the bright glowy ones. Well, if you could get to the inside, which we can, there's what you'd see on the inside. This is the dark matter. It would be black. It would not reflect, it would not absorb, it would not emit, and it will not concuss. So that is going to be the center of every atom's nucleus. And you will never see it until you've broken apart the way we did with light. Now they're breaking them apart at CERN by bang, huge tons of particles. And they see them, but they don't know that they're the light. We're looking at light, so we can see these particles. Now watch what happens when he puts that center core in there. He's going to add the positive. So now he's got a positive core surrounded by negatives. And in an atom, the surrounding negatives have just plenty. But the inside black matter really, really wants more. So this will try to get into it. But it'll say, no, we have enough surrounding us right now. We don't want you there. So what do we have here? Quantum distance. And you could put them all the way around here, and they'll all be around here, and they'll stay exactly where they're supposed to be. This is going to be right in between the electron neutrinos, basically, that surround the muon neutrinos, which is the core, which is the dark matter, which is this part right here. That's the dark matter. That's the core of every atom in every nucleus. And these can only get so close because the blackness is much more attractive than the whiteness is repulsive. So even though the white ones here on the outside, the glowy ones, which would be the electron neutrinos, they say, we can push you away, you can't come any closer. But this guy says, I will suck these things against me. So it's a fight between this and this to push that away. When there's enough of them around here, it becomes stable, as I showed you in the shaking. Boom, it's stable. Now more of them want to come in because this guy still wants more of them coming in. But they'll hang around way out on the outside. That's what the nature of matter is. That's the nature of electron flood theory. I know I've shown it, so I'm going to show you one last time and then we're going to close this up. Alright, that's the standard Bohr model. It's just nothing but a positive core. There's some neutrals in here, but it's still positive. These are all negatives. It's just impossible. It can't possibly work. This is what the real nature of every electron is. It's not a single glowy little particle. It is that, but it has attached a dark matter part. And they are the things that make everything up. So here is what Roger's model is this. It's not that. It's the dark matter goes to the center. The white ones surround that center core. Now, it's going to be completely balled up like this, with the white ones surrounding the dark center. And then there'll be other ones that want to get in. This would be a hydrogen, having 1,839 electrons in the core, and one more that is being pushed away, but it would try to get in. This is still trying to attract more. The dark matter is extremely gravitational. That is just gravitational as can be. And that's why they additionally suck in more and more particles, just like this will. You should come up and watch this. It's called Incredible Tractor Beam Magnets. Very, very cool. And it'll stay there. You can shake it around. And right now, that's just basically a, stable sort of thing laying around. But when you shake it, that's what heat is. Now it's starting to get heat. And the only reason it would shake is because something's trying to invade it. And it'll shake like that. And then when it takes off, that's real heat, fire. And then it's also light. When it goes flying away, look at that. Boom, that's light. All right, so basically that's about as close to an atom as you can get, the nucleus of an atom and its surrounding orbital electrons. And don't forget, they're all dipoles. Okay, my friends, this is Roger once again, and today it's time to put it all together. What does it mean? What the hell does it mean? If you've been following me, you understand there was giants on the earth, and I mean they were giant. This is a 3-foot-long fingertip on my property, DNA tested, absolutely 100% certain it's human. And not only do I have that one, and here's the DNA test from it. And there's actually 3 of them on here. 2 of them were giants, and 1 of them was our size. And it was excellent quality DNA. And I extracted it myself. And I didn't take my own blood or anything. This came right from the arteries. Excellent quality DNA sequence obtained from that gigantic fingertip in the lung. And here's the sequences and what they were, mitochondrial DNA. And he said it was absolutely 100% certain this was identical to mitochondrial human DNA. That's the mother's side. And it was a certified test by a very credible lab, and they did a magnificent job. And I know they took a lot of heat for doing this. And he said he stands by his results, but I had to make it absolutely certain that I was the one that did the extraction. I extracted it, and I sent them the stuff for DNA testing and sequencing, and they did their part. And that's what it was. And you can see that that was the fingernail side. This is where the grip skin side is, where the fingerprints are. See it? That's how perfect this thing is. Look at that. This is just one finger ridge like this is the same as my thumb, the same size as my thumb. It's huge, just gigantic, and it's human, and that's not the biggest ones there are. So we've got to start to take a look at what reality is. Here's what the reality is. There was giant humans. There was giant dragons. There was giant fish here. There's monsters. There's gods. There was aliens. And then there was Jesus. All of these things I'm pretty well certain about now. And they were all here basically at the same time. Wow. That's all I can say at this moment is wow.